As you can remember, on our previous lessons, we have learned very briefly main mechanical laws, or main laws of mechanics, and especially kinematics and dynamics. And now we are going to learn. We are going to learn we are going to start learning electricity and magnetism. As you can understand, electricity and magnetism is basics in basics in many technical applications, and especially for multimedia systems, because this subject is called physical basics of multimedia systems. And now we are going to learn some basics of electricity and magnetism. And as you can understand, electricity and magnetism is used in technology everywhere. Nowadays we can now imagine any device without electronics or something connected with magnetics. So it is important part in our education. So let's begin. As you know, maybe, I hope you know from school, that there are electric charges. And but it is necessary to remind you some main properties of electric charges. For example, it is known that every electric charge can be written by the formula Q. Is electric charge, is always equal to plus or minus E multiplied by N, where N is equal to 0 or 1 or 2. And so every charge can be described as quite a number of so-called elemental charges. What is E? E is elemental charge, and this is one of main physical constants, and it is well known and equal to, I'll type this. It is equal to 1,602,176 634 multiplied by 10 in minus 19 order. C. C is first letter Coulomb. Coulomb. It was a French scientist. French scientist French scientist who discovered many interesting things in mechanics and electricity. And C is first letter of this name. C is first letter of his name, and it also means unit of electric charge. Units of electric charge named by name of this scientist. Units are coulombs. Coulombs, and because of this we have letter C for units of electric charge. And what else? What else may you remember from school? What else? More properties of electric charge. It is law of conservation of electric charge. What does it mean? It means that if we have isolated system, the system that cannot exchange its electric charges with the environment. If the system cannot exchange its charges with the environment, it has constant electric charge. So the electric charge of the isolated system is constant. It is the law of charge conservation. The next property of electric charges is that there are two types of electric charges. We can call these types of electric charges as positive charges and negative electric charges. And it is necessary to remember that electric charges with different signs attract each other. So plus and minus, charges with plus and minus will always attract each other. Charges with plus and minus attract each other. And charges with the same sign, for example, plus and plus, or minus and minus, will always repel each other. So if we have electric charges, there is electrostatic interaction between them, and if the signs of charges are different, it will be attraction, and if the signs are the same, it will be repelling. What is necessary to say more? It is necessary to say that we just started to learn electrostatics. Electrostatics. What does it mean? It means that we are learning now electric field of fixed of fixed electric charges. And in other words, we are learning a constant electric field. And if we are talking about electrostatic interaction, it is necessary to describe this interaction mathematically. So we need some formula. We need some formula to make calculations, to solve exercises, and it is we can write a formula that is known from experiment. This law was discovered by French scientist Coulomb in 1785. This law was discovered, and according to this law, the force of electrostatic interaction can be written in this way. The force is equal to 1 divided by 4 p epsilon 0, 4p epsilon 0 modulus first point charge, second point charge, point charge is can be described like a point that has electric charge, or electric charge that is concentrated in one point. This is a useful model that sometimes helps very much to describe real physical systems. As you can remember, in mechanics, we have learned material point. Material point is a mass that concentrated in one point. And in electricity and magnetism, we are learning point charge. It is a charge that concentrated in one geometric point, and divided by r in second exponent. This is a scalar form of Coulomb's law. Coulomb's law. What is epsilon 0? Epsilon 0 is so-called electric constant. Epsilon 0, it is equal to 8,85 multiplied by 10 in minus 12 order farad divided by meters. What is farad? We will learn in future. It is a unit of capacity, and this is electric constant. Electric constant or vacuum permittivity. Vacuum permittivity or permittivity of free space. All of these terms you may see in literature or in internet. So it is necessary to know all of them. Or permittivity of free space. Permittivity of free space. Or permittivity of free space. I'll write this here. So epsilon zero is electric constant or vacuum permittivity or permittivity of free space. It is also one of fundamental constants, and it is necessary to notice that now we are learning electric field in vacuum. Electric field in vacuum. On our next lesson, we will study electric field in some substance in some media. But now we are learning properties of electric field, and especially electrostatic field in vacuum. So let's write this force of electrostatic interaction. Let's write this in vector form. How to do this? To do this, I will draw a picture. I'll draw a picture. With 2-point charges. For example, with radius vector r1 and r2. 2-point charges. 2-point charges that are equal q1 and q2. q1 and q2. And I want to find that the force that acts on charge q2 from charge q1. Force that acts on charge q2. Force that acts on charge q2. Force that acts on charge q2. And it is useful to draw this vector r that is equal to r with index 2 minus r with index 1. And of course, the force that acts on charge q2 can be drawn like this. This is force that acts on charge q2. And how to find this force? It can be found by formula. F is equal to 1 divided by 4p epsilon 0 multiplied by q1 q2 divided by modulus modulus of R in third order and multiplied by R. And it can also be written as 4p epsilon 0 q1 q2 divided by modulus of R2 minus R1 in third exponent and multiplied by the difference R2 minus R1 minus R1 minus R1. Do you have any questions? Of course, if we want to find force that acts on the charge Q1, we have to change places. We have to change places of this vectors, and in this way we will find the force that acts on the charge Q1. It can be written here. And I don't have enough space. On my screen. This is Coulomb's law. Coulomb's law. Coulomb's law. It allows us to find a force of electrostatic interaction between 2 point charges. And it is necessary to say that this formula is also can be used to calculate that force of electrostatic interaction between two charged balls or spheres. If the charge distributed symmetrically in relation to the centers. So if we have I'll draw a red frame. I'll draw a red frame to notice that it is important formula. Because this is important formula, I need this red frame. And it is necessary to say that if we have, for example, two balls with charge Q1, Q2, Q2, and the distance between their centers is equal to R. If the distance is equal to R, we can also use this formula. And this is very useful. Sometimes And it is necessary to know about this. Necessary to know about this. Okay. Let's find force that acts that is impressed upon a charge Q, and that is produced by the system of charges Q1, Q2, Q3, and etc. This force is equal to 1. It is equal to forces I sum from 1 to n f Fi is force that acts from the charge Qi on charge Q, and this is equal to sum I from 1 to n, from 1 to n, 1 divided by 4p epsilon 0 q I divided by modulus of r minus r with index I in third order r minus r I r minus r with lower index I, and we can write q divided by 4p epsilon 0 outside the sum. We can write this here. 4p epsilon 0. Q divided by 4p and epsilon 0 multiplied by sum I equal to 1 equal from sum of I from 1 to n, and here Q I divided by modulus of r minus r I in third order, r minus r I and what do we have here? Here we can divide left and right part of this formula. We can divide left and right parts by the charge Q. Let's do this. In result, we will obtain F divided by the charge Q. F divided by the charge Q is equal to 1 divided by 4p epsilon 0, 4p epsilon 0, sum from I equal to 1, I equal to 1, and the upper sign of this sum is n, sum from I to n, and here qi divided by r minus ri, minus ri is necessary to write vector in third order r minus ri, close bracket. And what do we have here? If you have a look closely at the right side, we can notice that this right side doesn't depend on Q, and it also doesn't depend on F. It doesn't depend on Q and doesn't depend on F. So we can sign this. We can sign this as E. We can sign this as E. And E is physical value that is known as electric field intensity, or simply electric field. Electric field intensity for the system of fixed electric charges, it can be found by formula. Electric field intensity. Electric field intensity. Electric field intensity. Electric field intensity can be found by formula. Electric field intensity of a system of fixed electric charges. 4p epsilon 0. 4p epsilon 0. Sum from I equal to 1 to n. Qi divided by r minus ri, r minus r. Where r? R is the radius vector of the point in which we want to calculate electric field intensity. This is r, and ri are radius vectors of electric charges qi, and electrostatic force that acts on charge q can be calculated by simple formula q multiplied by electric field intensity. Electric field intensity. Electric field intensity. Do you have any questions? Do you have any questions? No questions. Okay, let's imagine that we want to calculate electric field intensity that was produced by only one electric charge Qi. This electric field intensity can be found by formula 1 divided by 4p epsilon 0, 4p epsilon 0, 4p epsilon 0 qi qi I have made a mistake. It is necessary to correct this. Third order. Here in denominator we have third order, modulus in third order. It is necessary to take this into account. It is necessary to correct this. Yeah. Okay, that's good. Modulus R minus Ri in third order, and here R minus Ri and I need this. I don't need this anymore. So I can clean this from my screen. And if we substitute this here, we will obtain superposition principle for electric field intensity. Superposition principle. And according to this principle, electric field intensity can be calculated as a sum of from 1 to n, from 1 to n, of electric field intensities of that are parts of whole electric field. This is superposition principle. Okay, do you have any questions? Do you have any questions? Do you have any questions about this?
No, teacher.
No. Okay. So I will clean some space. I will clean some space on my screen. I'll clean some space because I need this. I need this to write more formula. Electrostatic field may be completely described by electric field intensity. So in other words, electric field intensity completely describes the electrostatic field, or electric field intensity gives us the whole information that we need to know about electrostatic field. And there is one more physical value. There is one more physical value that can give us the whole information about electrostatic field, and this value is electric potential. Maybe I have told you in mechanics that there are some fields. There are some fields of interaction that can be called potential fields. What is potential field? In this field, work of forces that produced by this field, work of these forces depends only on initial and final position of the point. And this is potential field. And maybe I have told that some cases of potential fields are gravity field. Gravity field is a potential field, and electrostatic field is also always potential field. Electrostatic field is a case of potential field, and it means that we can use such physical value as potential energy, and we can also use electric potential. Electric potential can be written as potential energy W is the potential energy of electric charge Q in electrostatic field. So potential energy of charge Q divided by the charge Q is equal to electrostatic potential. And why this potential is useful? It is useful because if you want to find work of electrostatic force, we can do it by simple formula. A is equal to Q. A is equal to Q multiplied by phi 1 minus phi 2. and it is equal to Q multiplied by U. Multiplied by U. Phi1, the potential of charge in or at initial point, or Phi2, potential at final point. So we can see that work depends only on initial and final position, and doesn't depend on path from initial to final position. Doesn't depend on the path, and it is very important. It is very important, and it is very useful. And U is the difference of potentials. Difference of potentials. U is the difference of potentials. So we can write this in the red frame. This is work of electrostatic force. It can be found via potential difference, and potential can be found as potential energy divided by electric charge. And it can I'll write this electric potential. Electric potential. Electric potential it can be found by this formula, and it can also be found via integral from R0 to R, from R0 to R, E electric field intensity, dl, and plus phi 0, phi 0. The second formula allows us to find a potential if we know electric field intensity. What is R0 and phi 0? R0 is some chosen point in space, and phi 0 some chosen value of electric potentials. Some chosen value of electric potential in point R0. Phi 0 if chosen value of potential at a point with radius vector R0, and R is a radius vector of the point in which we want to find potential. I think I'll show later an example of using this formula. In most number of cases we can we can use infinity instead of r0 and 0 instead of phi 0 in the most cases, but not everywhere. Not everywhere. Maybe I will tell a few words about this. And now it is necessary to say that units for electric field for electric potential is volts. Volts. Volt. Units for electric potentials. In short form, it will be just V. And units for electric field intensity is volts divided by meters. Volts divided by meters. Units for these physical values. Okay, let's have a look at electric field intensity and electric potential of one point charge Q. Of 1 point charge. Of 1 point charge. And let's place I have forgotten one thing to say. If we substitute this superposition for electric field intensity here, we can obtain new superposition principle for electric potential. It is also called superposition principle. It is also called superposition principle, but superposition principle for electric potential. For electric potential, phi is equal to sum from 1 to n phi I. So we can add electric potentials, and we can simply add electric field intensities according to the principle of superposition. So is it clear? Okay. Okay, let's continue. I'll clean some space, maybe later. So now I want to have a look at 1 point charge Q. 1 point charge Q, and I will put the origin. I will place the origin in this point charge. So in this case, radius vector r can be shown on the picture in this way. And according to the formula, we can write that for point charge we have E E is equal to 1 divided by 4p epsilon 0, 4p epsilon 0, 4p epsilon 0, q divided by modulus of r in third order, multiplied by r. It is electric field intensity for a point charge, for point charge q. Do you have any questions? No questions. Okay, so let's clean some free space on the screen and continue. This is a vector of electric field intensity, but I want to find electric potential. I want to find electric potential of a point charge, because electric field intensity is a vector value, and electric potential is a scalar value, and scalar value is simpler to deal with, so it is more useful because it is simpler to deal with it. And let's find this. I will decide. I will set that some initial point I will set as 0, and the potential at initial point I'll set, oh, no 0, sorry, no 0, infinity. I'll set this as infinity, and this I'll set as 0. This I'll set as 0. I'll set as 0. And according to this, I can write that phi is equal to integral r0 from r0 to r, e dl plus phi 0. Let's take into account this will be minus integral from infinity to r, e dl, and it is equal to, if we take into account this minus, we can write this with integral limits, with changed integral limits, changed places of integral limits. Integral from r to infinity e dl. And how to calculate this linear integral? To calculate it, we can remember, we can take into account that electrostatic field is always a potential field, and it means that we can choose the path from R to infinity. We can choose this path in any way we want to. We can choose any path we want to, and of course it is useful. It is useful to choose the path in such way that can make integral to be simpler. It can make integral simpler. So let's do this. How to choose the path? The best way to choose this path, this path is to choose this according to the condition, that is shown here, DL. What does it mean? It means that we can. I'll show this on the picture. E and DL. E and DL. It means it can be written in this way. And in this case, what do we have? In this case? In this case, we have scalar product. EDL is equal to DL cosine cos of 0 angle, and it is equal to EDL. This is the benefit. Of potential field. The benefit is we can calculate linear integral in simple way. We can calculate linear integral in simple way. We can read of vectors easily. We can read of vectors easily, and as a result, we will have, according to this, because the field is potential, we can write this without vectors. DL. And it is necessary to notice that we can do this only. We can do this for potential fields only. Not for every field, but only for potential fields. But because electrostatic field is always a potential field, we can always do this for electrostatic field. Okay, is it clear? Okay, let's continue. Let's continue. Let's make substitution. Integral from R to infinity. 1 divided by 4p epsilon 0 q divided by L insert exponent L and dl. We have changed R to L because here the variable is signed by L. So because of this we have changed R by L. So I can get q divided by 4p epsilon 0 from the integral. I can write it outside the integral from R to infinity dl divided by L in second order. And how to calculate this integral? It is necessary to remember calculus. Maybe from your first or second year at university. And if we remember calculus, we can write this integral. We can write this integral via limit. Via limit a intends to infinity, integral from R to A, dl divided by L in second order. And this is equal to minus q divided by 4p epsilon 0, limit a tends to infinity, 1 divided by L from R to A. And we can substitute our limits. Minus q divided by 4p epsilon 0 divided by 4p epsilon 0 limit a to infinity, and in brackets we have 1 divided by a minus 1 divided by R. Of course, if a tends to infinity, 1 divided by a will tend to 0. And this is equal to 1 divided by 4p epsilon 0, q divided by R. Divided by R. Divided by R. So, do you have any questions? Do you have any questions? Okay. One more thing it is necessary to say. It is necessary to say that we can set R0 and Phi0 like this. We can set these values like this only in the case when charges are in a limited part of space. If charge distribution is unlimited in space, we cannot use these values because the integral here will be infinite. So if for example, if we have infinite charged line or infinite charged plane, we have to use some other values for R0 and Phi0. And what can we say? We have obtained potential of point charge. Potential of point charge. We have obtained potential of point electric charge. Potential of point electric charge. I have cleaned this, but okay, I will write this one more time. 1 divided by 4 P epsilon 0, 4 P epsilon 0 Q divided by R. Divided by R. Potential of point charge. Point charge. If you know, electric field intensity and potential of point charge, theoretically we can find field and potential for any system of electric charges by using superposition principle for a point charge. For a point charge. For a point charge, we have this, but maybe it is better to use blue frame because it is not a fundamental law, but it is important formulas. These are important formulas that we will use to solve exercises. Okay, and one more questions. We have just find a potential of point charge from electric field intensity of point charge. But if we have another opposite problem, if we know electric potential and we have to find we have to find electric field intensity. How to do this? How to do this? And this can be done. This can be done by the next formula. E is equal to minus gradient of electric potential. Minus gradient of electric potential. Let's have a look at example. So I will use this to find this by this formula. Let's try to do this. E is equal to minus gradient from phi, and it is equal to minus d phi by d x I plus d phi by d y j plus d phi by d z by dz k and let's substitute. In result, we will obtain minus 1 divided by 4 p epsilon 0, 4 p epsilon 0. Here open bracket d by dx 1 divided by r e plus d by d y in brackets 1 divided by r, and sorry, word is necessary to be written, and plus d by d z in brackets 1 divided by r. Word key vector. Okay, how to calculate this? To calculate this, it is necessary to remember that r is equal to modulus of r, and it is equal to square root of x in second exponent plus y in second exponent plus z in second exponent. So it means that d by dx 1 divided by r is equal to d by dx 1 divided by square root plus y in second order plus z in second order plus z in second order. And let's find this derivative, partial derivative d by dx. This is equal to minus 1 divided by 2 square roots of x in second order plus y in second order plus z in second order, multiplied by the derivative from x, y, z in second orders, and this will be 2x. And what do we have? We have minus x divided by square root. Sorry, here will be third order. X in second order, y in second order plus z in second order in the third order. And what we can do, we can substitute this here, and it will be minus x divided by r in third order. And okay, let's leave this like in this form. Do you have any questions about this? No questions. No questions. Okay. Okay, that's great. That's great. That's great. We can use this here. We can use this here to calculate this gradient. It will be minus 1 divided by 4p epsilon 0, 4p epsilon 0, 4p epsilon 0, and here we have minus x divided by r in third order, and in the same way we can calculate the other terms. It will be minus y divided by r in third order, and minus z divided by r in third order k. And let's write this. Let's write this. I have forgotten something. I have forgotten charge Q. Of course, I have forgotten the charge Q. Yes. And now I hope that's all right. So Q divided by 4p epsilon 0. Q divided by 4p epsilon 0. And here we have xi plus yj plus zk are in third order, and this can be written. This can be written as 1 divided by 4 p epsilon 0 epsilon 0 q divided by modulus of r in third order and multiplied by r vector. So as you can remember, we have obtained the same relation, the same formula as here. So we can get electric potential from electric field intensity, or opposite, we can get electric field intensity from electric potential. So both electric field intensity and electric field intensity give us the whole information about electrostatic field. Do you have any questions? Do you have any questions? So if you don't have any questions, I have to thank you for your attention. Thank you for your attention. And I hope to see you next week.